Assalamualaikum warahmatullahi wabarakatuh. We are from Group POWERTECHS. We would like to present our projects on heat transfer. First of all, I introduce my members as MOHAMAD RASYIDAN and also SUFIYAN RAWI. As my name is Muhammad AZMEER bin Muhammad ASRY. Let's go into my part. My part contains of 7.1, 7.2, 7.3. 7.1, we go into the first introduction to the radiation. Okay, as you can see in the slides, radiation does not require the presence of material medium to occur. Next, according to the Maxwell theory, energy transfer takes place via electromagnetic wave in radiation. The wavelength formula is equal to C divided by V. C is the speed of light and V is the frequency. Besides that, we also have the formula as the figure this C0 divided by N. C0 is a constant value 2.7779 divided by 10 of power of X meter per second, and N is the index of refractions. N is equal to 1 for S and others such as the figures. Next, Einstein has postulated another theory for electromagnetic radiation, which is, as you can see in this slide, which is E H divided by times by V, which we call the E as a photons. H is the constant value as 6.625 times by 10 power of 34. Next, as you can see in this slide, we introduce you by the thermal radiation wave is a narrow band on electromagnetic wavestrom. It's contained as like ultraviolet, thermal radiation, infrared, and microwave up to 10 of power 2 on above. Okay, next we go into the phenomena of radiation in the this slide. Okay, the thermal radiation emission is a direct result of vibration and rotational motion of molecule, atom, and electron of a substance. The temperature measure of this activity, thus the rate of thermal radiation emission increase when increasing the temperature. Okay, the thermal radiation we call as a volumetric phenomena. However, for opaque solid such as metal, radiation is considered to be a surface phenomena since the radiation emitted by the interior region never reach the surface. Note that the radiation characteristic of surface can be changed completely by applying thin layer on the coating on them. Next, we move into the black body and grey body radiations. As you can see in this slide, the black body is defined as a perfect emitter and absorber of radiation. At a specific temperature and wavelength, no surface can emit more energy than a black body. A black body given by this formula as black body emissive power, and the Stephen-Boltzmann constant as 5.670 power of negative X. As you can see in the figures, uniform black body and real body non-uniforms. Next, for the formula, the spectral black body emissive power, as the figures of this slide, you can see the structure of the formulas. So the next slide, we move into the next slide, which is we can see the Wiens displacement law, which is 2897 μm kelvins. For the next slide, we move into the total body emissive power EB by given these formulas. So in the figures also you can see as the incident light into the impact into the, and then reflects into the red colors. And also the next slide, we move into the radiation energy emitted by black body per unit over area as the formulas. And also for the to avoid numerical integration of Planck equation, the new formula as the figures they are introduced, such as this formula is important because we want to know how to read in the table next video. So we move into the grey body radiation. Grey body radiation is non-ideal emitter or an imperfect radiator as this slide. A grey body will absorb some of energy it will receive, reflect some of energy it will receive, emit the energy it absorb. Next, we move into this example of the grey body example. We can see the temperature of filaments light bulb 250K is set as a filament fall in the visible range. So visible range we spectrum extend from 0.4 until 0.76, So by using the proper formulas, we get 100 μm's and 1900 μm. So by referring the tables, we can identify the F1 and F2, and we apply the formula as the figure and get 0.05271. Now we move into the 7.3 radiation properties. Radiation properties is focusing on the emission and absorption characteristic of the surface. Okay, for the emissivity is defined as the ratio of radiation emitted by the surface at a given temperature to the radiation emitted by a black body at the same temperature. F the emissivity measure of how closely a surface approaches black body as a once. Okay, emissivity can divide by 2, which is spectral emissivity and also directional emissivity at specific directions. Next, for the next slide, we can see on the several formula as spectral directional emissivity, total directional emissivity, spectral hemispherical emissivity, and total hemispherical emissivity. Next, we move into the next slide. We can see at the figure 12.24 is approximate the actual variation of emissivity with wavelength by a step function. Besides that, the emissivity also contained as emissivity 1, emissivity 2, emissivity 3, depending on the wavelengths. Next, we move into the next slide, which is a surface is said to be diffuse if the properties are independent of direction, and gray is if its properties are independent of wavelengths. Next, we can see on the figures 12.25 the effect of diffuse and gray approximate of the intensity of surface. Besides that, on the next slide, we can see the comparison of the emissivity and emissive power. For the A is the emissivity, and for B is the emissive power. Next, for the next slide, we move into the 3 different formulas, which is absorptivity, reflectivity, and transmissivity. Is given by the specific formula as the slides. Next, for the G symbol we call as the irradiation, which is radiation flux incident on the surface. Next, the absorptivity and reflectivity and transmissivity we plus on each other and become as a normal G as these formulas. Next, for the next slide, that contains several difference of types of the absorptivity and also the directional reflectivity. As you can see, as a contains as spectral hemispherical absorptivity, spectral hemispherical reflectivity, and spectral hemispherical transmissivity. Next, and in the right figures, 12.32, we can see a different type of reflection, as A is the actual or irregular, B diffuse, and C is spectral or mirror lights. Next, in the next slide, we move into the next slide. In the practice surface are assumed to reflect in perfectly spectral or diffuse manner. Spectral means as the angle of reflection equal to angle incident of radiation beams. The diffuse reflection defined as the radiation is reflected equal in all directions. As you can see in the figures 12.35, the absorptivity is different from the other results, which are 0.9 from the school and 0.6 from suns. So it depends on the source. For the next slide, as the Kirchhoff's law. Kirchhoff's law can be defined as the total hemispherical emissivity equal to the total hemispherical absorptivity as the figures. It's called the spectral form of Kirchhoff's law. This Kirchhoff's law is important as to identify the example and solutions by using this Kirchhoff's law. Okay, thank you. That's all from me. I hope you enjoy, and we move into the next subchapter.
Assalamualaikum. My name is SUFIYAN bin RAWI. My metric number is DD170016. Okay, for heat transfer group assignment, I will present about three subtopics, which are spectral and direction dependency, total hemispheric properties, and radiation view factor. Okay, first I will explain about spectral and directional dependency. Okay, spectral quantity is a radiation quantity that consider the variation of radiation with wavelength and direction. The word spectral mean is at a given wavelength. Spectral ratio intensity can be expressed as this equation. Okay. And Max Planck has determined an equation to express a spectral intensity of radiation emitted by a black body at an absolute temperature and a specific wavelength, which is this equation. Okay, next I will talk about the total hemispheric properties. Okay, when radiation strike a surface, the radiation will separate to three parts, which are the radiation will be absorbed, radiation will be reflected, and radiation will be transmitted into the ground. So these are the formula that involved in these three parts. Okay, G in the equation is represent the radiation energy. So G absorb is radiation energy absorbed. G reflect, G-REF is radiation energy reflect. GTR is radiation energy transmitted. Okay, the first law of thermodynamics require the sum of GABS, GREF, and GTR is equal to incident radiation, which is represent in this equation. Okay, this equation will be divided in term of G and will resulting this equation. And next, the opaque object will be assumed as 0, and thus we will obtain this equation. From this relation, it will enable us to determine absorptivity and reflexivity of an opaque surface. Okay, these are the definition of total hemispherical properties. Okay, next I will explain about radiation view factor. Okay, view factor is a geometric quantity and it is independent to surface properties and temperature. So it has two types, which are diffuse view factor and specular view factor. Okay, diffuse view factor is view factor that based on assumption that the surface are diffuse emit and diffuse reflector. Okay, specular view factor is view factor based on the assumption that the surface are diffuse emitted by specular reflector. Okay, the useful of view factor is it can be used to analyze radiation because it allow us to express fraction of radiation leaving a surface. Hundreds of common geometries are evaluated and the results are in given analytical graphical and tabular form. Okay, these are the example of view factor expression for some common geometries of finite size. So these three, okay. Okay, next I will talk about view factor relation. Radiation analysis and an enclosed consisting of n surface require the evaluation of n square view factor. Once a sufficient number of view factor are available, the rest of them can be determined by utilizing some fundamental relation of view factor. So these are the reciprocative relation. So next we have summation rule. Okay, this rule is the sum of view factor for surface I of an enclosed to all surface of the enclosure including itself must equal unity. Okay, these are the example figure and these are the equation involved. Next, the superposition rule. The view factor from a surface I to a surface J is equal to the sum of the view factor from surface I to part of surface J. So these are the figure. So these are the equation involved. So next, the symmetry rule. Two or more surface that possess symmetrical about a 30 surface will have identical view factor from the surface. If the surface J and K are symmetrical about the surface I, then this involved, and this the example of figure. Okay, lastly, view factor between infinity long surface, the cross-setting method. Channel and duct that are very long in one direction relative to the other direction can be considered to be two-dimensional. Those geometry can be modeled as being infinity long, and the two factor between their surface can be determined by the simple cross-string method. So these are the equation formula involved. Okay, that's all from me. Thank you.
Assalamualaikum and salam sejahtera. My name is MOHAMAD RAHMAT. Okay, today for the heat transfer through assignment, I will talk about radiation heat transfer between two surfaces. First of all, there are several types of surfaces that can be used in this subchapter, which is black surface and gray surface. For the black surface, for the overall formula heat transfer, Q dot 1 to Q dot 2 equal to radiation leaving the entire surface 1 that strikes surface 2 minus radiation surface leaving the entire surface 2 that strikes surface 1. Okay, as you can see below is the overall formula that can be used in this subtopic. For the gray surface, the formula that being discussed before can be used for the gray surface. Okay, the surface must be opaque, diffuse, and gray, and it also must isothermal and uniform. For the radiosity, as you can see, Ji equal to radiation emitted by surface I plus radiation reflected by surface I. Okay, for the you can see the figure 32. Incident radiation reflect from the surface to the refraction radiant and emitted radiation. Net radiation heat transfer to or from a surface. Q dot I equal to radiation leaving entire surface I minus radiation incident on entire surface I. Then Q dot I also equal to AI Ji minus Ji minus epsilon I E Bi per 1 minus Si. For the surface resistance formula, Ri equal to 1 minus sigma I per Ai sigma I. There can see that resistance network have two types, which is series and parallel. We can use by concept of electricity to simplify the resistance. For the parallel, we are going to use parallel formula, and series we're going to use series formula. Then for the conclusion, we can make that radiation using the light to transfer the heat to the other surface. It's not using medium such as solid surface, solid medium, but it use convection medium such as gas. Okay, that's all for our group. Thank you for watching our video. Thank you.